Hello, this is my first video here in YouTube. Welcome to my channel. We're going to talk about tensors. No, not this lamp from Staples. So Google announced a chip that will be inside their upcoming Pixel 6. They got sick of those rumors spreading about the Whitechapel chip, so they invited some YouTubers to see a prototype of the Pixel 6 and told them a few things about it. The chip has an official name, Tensor. It was named after Google's AI chips called TPU or Tensor Processing Units. One of those videos is by Gary Sims. He did not get to see the Pixel prototype, but he talked about the chip. Gary said that naming it Tensor is a bad idea because so many things are named with it. And I agree with him. One thing he mentioned was the dictionary definition of tensor, a mathematical object analogous to, but more general than a vector, represented by an array of components that are functions of the coordinates of a space. When I saw this, I was like, that looks familiar. I guess tensor is an original math word, and it is what I thought it was. Today I'm going to show you what tensor is from the point of view of differential geometry. There is an algebra version of tensors, and by algebra I mean abstract algebra. It is more general, but I will not talk about that. We're going to go over the differential geometry tensor. When I thought of making this video, I searched for videos about tensor to see if someone made a video about it. There were plenty. Some are about physics, some are about machine learning, some are about TensorFlow, the language. Many of them say that a tensor is a generalization of a matrix, which they say is a generalization of vectors. They all look vectors to me. Here are my main references. A book by Mike Spivak and a book by Jack Lee. A tensor looks like a matrix. A matrix can be one column or one row. No, not that. Here, a row matrix. Sometimes these are called column vector or a row vector. What can we do with matrices? We can add or subtract two matrices of the same size. We can scale them. We can multiply two of them provided that the sizes are compatible. A tensor can look like these. They have rows and columns of numbers, but they can also have layers of numbers. So this is a 2 by 3 by 4 tensor now. 2 by 3 by 1, 2, 3, 4 tensor. Like 4 layers. And they can even have more bys, like 2 by 2 by 2 by 2 tensor. Okay, 2 by 2 by 2 by 2 tensor. Just like matrices, we can add two tensors of the same size. We can scale tensors, but we don't really multiply them like we do with matrices. More on that later. What do we do with them? We plug vectors into them. The output is a number, like one number or a 1 by 1 matrix. For example, this is a 2 by 3 tensor. We plug a pair of two-dimensional vector and a three-dimensional vector. The output should be one number. We plug vectors like these. This go to here. This go to here. The tensor goes to the middle, and we multiply them like your ordinary matrix. The output is one number. Now, what if we have a tensor with layers, like a 2 by 3 by 3? Like this. Okay, so since this is a 2 by 3 by 3 tensor, we plug a 2D vector, a 3D vector, and another 3D vector in that order. The output is one number. I just made up the word layers. Nobody really calls it like that. So how do we deal with this? So we take this first column and we put labels in them. So this first layer here, we put labels. We take the first column and we put 1, 2 here. Like that. We do that the same for the next columns. 1, 2, 1, 2. Now, the first row, we put 1 on all of them. No, we put 1, 2, 3. Okay, and the second, we put 1, 2, 3 as well. 1, 2, 3. Just as we would label a matrix. Now, since this is the first layer, we all put 1 in them. 1, 1, 1, 1, 1, 1. Okay, now do the same with the second layer. 1, 2, 1, 2, 1, 2. 1, 2, 3. 1, 2, 3. All of these are second layer. So we put 2 on all of them. Like that. And then do the same thing with the third layer. Now, if you notice, the labels that we have 3 numbers in them. So A sub some number, some number, some number. We don't really use the square boxes, but what we use are letters, I, J, K, or we call them indices. Now, how do we turn all these into one number given the vectors? Here's how we do it. We take 1, 2, 3 here, for example. A1, 2, 3 is -4. Let's go to the next page. So A1, 2, 3 is -4. Multiply that by the first entry of the first vector. So that's 3. So the next is 2 here. We take the second entry of the second vector, which is 2. Next, we take the third entry of the third vector, which is -2. We multiply them all out, and the result is 48. Okay, so there are 18 total multiplications here. And we did already one. Just do that 17 more times. The result is all these. Okay, so for example, A113 is 3. The first coordinate of the first vector is 3. The first coordinate of the second vector is also 3. The third coordinate of the third vector is -2. So here's what we did, the 1, 2, 3. Where's the 1, 2, 3? Here. Okay. So we do all these multiplications and then add them all up. The result is -210. So if we plug the vectors, these vectors, into this 2 by 3 by 3 tensor, the output is -210. Now, what if we have a 2 by 2 by 2 by 2 tensor? Okay, so we do the same thing. We put labels in them. So we should take note of the order. This is the row. This is the column. So 2 columns, 2 rows. And then this is the first layer, second layer. So first layer, second layer, and then next sublayer, these 2. Okay, so we put labels in them like before, and suppose we need to plug these vectors in that order, well, we also put labels in them. And we do the same thing with 2 by 3 by 3. We mix and match them. Well, we match them properly. Do the multiplication, then add them all up. So once you add these all up, you get 2. So that's tensor for you. It's a function that takes an ordered finite amount of vectors and the output is one number. Can we have a tensor that takes only one vector as an input? Yes. It's called the dual of a vector space V. If V is a vector space, its dual is V upper star, which is the set of linear functions from V to R, or whatever field over which V is. Here's an example. We take this row vector here, 3, -1, 2, as a tensor. We plug a three-dimensional column vector into it. Say we plug 1, 2, 3 to 3, -1, 2. Here's how we do it. We multiply them like this. Like an ordinary matrices. So 3, -1, 2 times 1, 2, 3 is 7. The output is still one number. Yes, it's like inner product with a constant. So this tensor, 3, -1, 2, is a function from R3 to R that takes the vector xyz into 3x plus -1y plus 2z. In general, a tensor is a multilinear function from a set of a Cartesian product of vector spaces to the set of real numbers. That is the definition of tensor in the view of differential geometry. If V and W are vector spaces over the real numbers, a tensor is a function from V cross W to R that is multilinear. What is multilinear? It's this. We can distribute F over the plus in V. We can distribute the F over the plus in W. We can pull scaling of vectors out of F to outside. Notice that nothing here mentions matrices, entries, or arrays. A tensor can also take more than two vector spaces like V1, V2, V3, and so on up to Vn. Boys and girls, do not show this to your parents unless your pure parents are mathematicians. This is what multilinear means. We use this circled X notation for tensor products. It looks like the logo of X-Men. Marvel Comics was years ahead of Google when it comes to artificial intelligence. And we use it like this. If F and G are tensors, then F tensor product with G, that's how we read it, is an n plus k tensor. How do we plug vectors to F tensor G? We take the first n vectors plug it to F, take the rest of the vectors, plug it to G, and then multiply them. You can also see this X-Men logo in some videos talking about tensors. Take note that in differential geometry, those vector spaces are usually the same. Okay, so they have the same dimension. If a tensor takes n ordered vectors from the same vector space, we call n the rank of f. So f is an n tensor. It can also take elements of the dual space. They're called covectors. I just didn't go over them here. So if we have L tuples of covectors and K tuples of the vector elements, or well, just vectors, and if we want to plug it to a tensor, that is called a KL type tensor. And then there's this identification. So this is the old school square matrices, and this is this set of type 1 tensor. And in differential geometry, they don't make distinction between the two, even though they're different. So that's tensor. How is this related to machine learning, neural network, or artificial intelligence? I have no idea. If you know, please make a video explaining the connection, no pun intended, between them and post the link in the comments. Maybe Google and Nvidia just took the word and stuck with it. I don't really know. Did you know that the determinant is a tensor? So the determinant takes a square matrix and gives a number like this. How is this a tensor? The input vectors are the columns of the matrix. For example, here's a 2x2 matrix. Break this matrix into columns. Then do this. So this 0, 1, -1, 0 is the matrix form of a 2x2 determinant tensor. If you multiply this out, the result is AD minus CB, which is the formula they tell us in a linear algebra class. For a 3x3 matrix, we would need a tensor with 3 input vectors. Each of the vectors has 3 numbers. That means we need a 3x3x3 tensor. We need 3 times 3 times 3 entries. That's 27. The good thing is that most of the 27 numbers are zeros. We only need 6 numbers that are not 0. Let's put labels on them like before. The idea with determinants is that whenever we see 2 same indices like these: 1 1 1 2 2 3 3, 1 1 2 2 3 3. The entries are 0. Same thing for this: 2 1 1 3 1 1. Also the same thing for 1 2 1, since the 1 is repeated. Same thing for the next layer. This one has 2 3 2. The entry is 0. The only time the entry is not 0 is when the indices are different, like 1 2 3. There are only 6 of them: 1 2 3, 2 1 3, 3 1 2, 1 3 2, 3 2 1, and 2 3 1. We start with 1 2 3. The entry is 1, like this. If we switch just two numbers, let's say 2 and 3, so we got that 1 3 2. If we switch just one pair of two numbers, the entry is -1, like this. Now for 2 1 3, that's like switching 1 and 2 from 1 2 3. So 2 1 3 is obtained from 1 2 3 by switching 1 and 2. So the A213 has an entry of -1. Now for 231, that's switching 1 and 3 from 2 1 3. So let's do it again. We're gonna do 2 3 1. We start with 1 2 3. We need a 2 3 1. We can get that by switching 1 and 2 and then switching 1 and 3. If we need two switches, the entry is +1. So for 2 3 1, where's 2 3 1? Here, the entry is +1. If we had to do even number of switches or transpositions, the entry is 1. For odd number of transposition, the entry is -1. So here are the results, like this and that. This one should be -1, I think. Okay, and this one is -1. Okay, so the results are here. The rest are zeros. So the determinant of a 3 by 3 matrix is this. ADG is the first vector, BEH is the second vector, CFI is the third vector. If we plug these to these tensors, we get this one. 1 AEI minus 1 AHF minus DBI plus DHC minus GEC plus GBF. Now, for a 4 by 4 matrix, we would need a 4 by 4 by 4 by 4 tensor. That's 256 numbers. Good thing most of them are zeros, but we still need 4 factorial non-zero numbers. That would be your homework. See if you get the same numbers as mine. If you have taken linear algebra, maybe you now appreciate why using row operations to compute the determinant is more efficient and less boring than this combinatorial way of computing the determinant. My question for you is this. Now that we see that the determinant is a tensor, thus Cramer's rule have less complexity than Gaussian elimination when using an NVIDIA RTX card. I don't know the answer. I'm not tech savvy. That's it for this video. Thank you. I hope to see you again sometime later. Bye.